This video will try to give a quick overview of elementary notions in probability theory, like sample space, event, probability, conditional probability, independent events, and Bayes theorem. Sample space. In probability theory, the sample space is the set of all possible outcomes of an experiment, usually denoted as omega. It can be a finite set, like for tossing a coin or throwing a die. It can be countably infinite, like for estimating the size of a bee population. Or even uncountably infinite, like for estimating a land area. Event. An event is a subset of the sample space. If, for a coin, the sample space is head-tail, then an event A could be the one in which the outcome is head, and event B the one in which the outcome is tail. But omega itself is a valid event as well. It is the certain event in which the coin is either head or tail. And finally, the empty set is also a valid event that models impossible outcomes. For throwing a die, an event could be one of the sides, for instance side 1 or 5, or the event the outcome is odd, which is another way of describing the set 1, 3, 5, or the event the outcome is greater than 3, and so on for any valid subset, including of course the sample space itself and the empty set. The total number of unique events is therefore equal to the total number of unique subsets, which in this case is 2 to the power of 6. For uncountably infinite sample spaces, the events can be intervals. In general, events in infinite sample spaces require certain properties like being closed under complementation and countable union, and their rigorous definition is more complex. Even so, since events are subsets, we can perform the usual set operations with events and represent them using diagrams. For example, for a six-sided die, we can represent omega as a rectangle and events like areas within. If event A is the die is less than 4, and event B is the die is an odd value, we can represent the event the die is less than 4 and is an odd value as the intersection between A and B, which is the set 1, 3. Similarly, the event either A or B happen can be represented as a union of sets. Also, the complement is applicable to events just like to any other sets. Events A and B are called disjoint or mutually exclusive if A and B have no outcomes in common, or, in set notation, if their intersection is the empty set. In this example, the event the die is even and the die is 1 are mutually exclusive or disjoint. Probability. The probability is a function which assigns to any event from omega a value between 0 and 1 such that probability of omega is 1 and the probability of A union B is equal to the probability of A plus the probability of B if A and B are disjoint. Intuitively, this is like working with areas on the diagram, and the probability of A is like the area of A divided by the area of omega. An important and immediate property is that for two events which are not disjoint, we have to subtract the probability of the intersection, which otherwise would be counted twice, just like if we were to add up two overlapping areas. Conditional probability. Conditional probability is a measure of the probability of an event occurring, given that another event has already occurred. Intuitively, this is like reducing the sample space from omega to B. So if a normal probability can be thought of as the area of A over the area of omega, then a conditional probability can be thought of as the area of A that is also part of B over the area of B. This intuitively explains the definition, which is precisely the probability of the intersection over the probability of B. Despite its simple mathematical definition, the conditional probability represents a very deep concept in statistics and machine learning, because it can be thought of as a basic model for learning by adjusting prior beliefs to new evidence. For example, if we're trying to find if someone's birthday is during summer, we could say that the sample space is the set of all 12 months, so the probability would be 3 in 12, or 0.25. But if we also learn that the birthday is on the 31st, the valid candidates now are only the months with 31 days, 7 in total. Out of these, only 2 are in the summer, so our conditional probability is now 2 over 7, or about 0.29. So after learning this new information, the probability of A changed from 0.25 to 0.29. Independent events. Of course, not all new information will be relevant. If, in that example, instead of being born on the 31st, the person was born on the 21st, this would tell us nothing about the month being in the summer or not, since any month has 21 days. Our probability thus remains unchanged at 0.25. These events are called independent. In fact, by definition, two events are independent if their conditional probability is equal to their probability. Note the distinction between disjoint and independent. If two events are disjoint, they are mutually exclusive. So, knowing that B happened gives us a lot of information about A. In fact, it tells us that the probability of A is now 0. But for independent events, the proportion of A in B needs to be the same as the proportion of A in omega. So they cannot be disjoint, as some of A must belong to B. Bayes Theorem. Arguably the most famous theorem in probability theory, Bayes' theorem provides an alternative way of calculating a conditional probability. To use the typical example, let's consider the events A, the email is spam, and B, the email contains the word free. The probability that the email is spam, given that it contains the word free, is, according to the definition, the probability of the intersection of A and B over the probability of B. But in practice, measuring the probability that an email is spam and it contains the word free is unnecessarily complex because technically it requires evaluating all emails for the matching criteria. However, the probability of the intersection can be expressed like this just based on the definition of conditional probability, and can be substituted in the original definition, and the result is Bayes' theorem. This formula establishes a link between the probability of A before knowing that B happened, also known as prior probability, and the probability of A knowing that B happened, also called posterior probability. This relationship directly shows how a belief, expressed as a probability, changes as new information becomes available. Of course, if the new information is not relevant, in other words, if A and B are independent, and the probability of B given A is just the probability of B, as we've already seen, and the probability of A remains unchanged. I hope this has been useful, and please check the links in the description for additional references. Thanks.